Right, now we are in the continuation. So let's come back to our infinite number series. So this is a new limit procedure, right? We want to deal with infinite sums, but is there anything new there? No, we simply take the partial sums, so always ending with some k, and then, so that's the sk, and then we simply consider the limit. So it's simply only a limit of a sequence of partial sums, and we say that the sum diverges to infinity or minus infinity if the limit is such, and if it doesn't converge at all, then we say that it oscillates. And the infinite number series, so the infinite sums but of scalars of numbers, the numbers can be, as usual, either reals or complex numbers, we don't care. So that's a very, very useful object, and very often we find this object. And actually whenever we compute something which is not directly a polynomial, what we do is we approximate something which would be essentially the infinite sum of some approximating small bits, but we always end with some k already, and we assume this is an approximation good enough. So in some sense the infinite sums are an abstract concept which allows us to deal with things and make estimates how good our numerical procedures and our countings and computings is, right? So and that's very crucial for the pure mathematical approach, to have such abstract objects you can work with, which then are used to understand your approximate approach to real world. So the corollary of the definition automatically is that you can add such infinite sums simply by adding the components, and by the general properties of limits this must hold true. So the sum is obtained as sum, and the scalar multiple is obtained as scalar multiple. So in particular, just in parallel to what we do in the other course, you see that we simply have got a vector space, a big vector space of the infinite sums. So, and some of them are converging, and the converging ones form a nice vector subspace, a vector subspace of those which converge. And you see from this corollary that it really is a vector subspace. So there is a very important observation coming now. So basically, whenever I've got such a thing like again like a sum of scalars, then I can take instead the absolute value of the scalars. So it's not only important for complex numbers but also for the reals, because if I take the absolute value, I simply ignore the signs. And you can imagine that if I have a sum where I always just add something and then subtract something and then add something, it might oscillate to some fixed value, right? But it's much more strong to believe that it converges if it would converge also in the absolute values, because then it means that the individual items I'm adding must be smaller and smaller at much faster pace. And it's clear just from the triangular equality that if you just look at the difference of the partial sums, right? So this Sm minus Sn, then it's simply the sum of the m minus n terms in absolute value, and you can use the triangular inequality, so it will be always bigger if you just take the sum separately, right? And therefore, if this should converge, is the same requirement as having it Cauchy sequence, right? The partial sums must form a Cauchy sequence, because we are in real numbers or complex numbers, and therefore every Cauchy sequence will converge. And you see that the partial sums for the absolute values will, if it's a Cauchy sequence, it will imply that the original one was as well. And therefore we know that the absolutely convergent series always converge. And for the absolute convergent series you have a nice set of properties. So here in the first one it's just what we knew already, but the point is that the addition of two absolutely convergent ones is again absolutely convergent ones. The same with difference, but more interestingly it works nicely with the product. So you can look at it like you simply always multiply an with big M, so that the sum of the indices would be going from 0 to n, right? And this goes for n going from 0 to infinity. So the sum should be n, and the n goes from 0 to infinity, right? So this is just the sum of all which bring us n. And the most important fact is the fourth one, or not most, but very important, is that if the sum converges absolutely, then the summing doesn't depend. So the result of our addition of the partial sums, so the limiting value, does not depend on the ordering. That's very crucial and very interesting, in particular in the context of the fact that if the sum does not converge absolutely, then the opposite holds. Then you can imagine if you have a sum of ai, I goes from 0 to infinity, and this would be equal to sum a, but sum absolute value of ai is infinity, right? You know this is strictly increasing sequence of the partial sums, because we not decreasing, right? So it must have the limit. It's the supremum might be infinity. So let's take this case. So both at the same time. What does it mean? It means that here in the sum I must have pretty many of the positive and negative values of ai, or in complex numbers it would be just in all directions, so that they can cancel each other to come finally to a. But now if it's just real, right? So I can always say, well, if I would aim at ending at b, I can simply take the ai's into two heaps. One of them will be the positive ones, one of them will be the negative ones, and from both of them I will take them by the size of them. I will order them by size. So I will take the big ones first, and then I always take so many big ones from the positive ai's to be above b, and there must be enough of those, because we know that the sum of all of the positive ones and the absolute value of the negative ones is infinity, right? Then I take as many of the negative ones to be below b, and I repeat this iteratively until infinity, and with some care you can prove that you can really always get to any b, right? So that's very stunning. So that's called the Riemann theorem. But let's go on. So here is some. So technically you have to prove everything, so I will not go into the details, but there are some very simple tests, and the simple tests say, well, are going along the line that you have got what we call the squeeze theorems, right? So you had one of the sequences and another sequence, and they had the same limit point here, so whatever you would have squeezed between those two must have the same limit, right? And basically following this philosophy we get all these beautiful results. So first of all, if the series converges, then necessarily the individual elements an must be smaller and smaller, and their limit must be 0. No excuse. That's a necessary condition, right? Then we have got the comparison test. So if we know that T is a series which has got just positive real numbers, so the series T converges absolutely all the time, and if I know that the absolute values of A are less than b, then S must converge absolutely, right? So you can compare only individual terms, and it tells you in absolute values, right? It tells you that it converges absolutely. The other way around, if T diverges and the ANs are in absolute value bigger than BN, then S does not converge absolutely, right? So it might converge, but not absolutely. So that's the absolutely basics. All the others come from this one. So the limit comparison test. So if we compare our ANs with absolutely convergent BNs, which are the positive ones, and if we know that asymptotically, so for n going to infinity, the ratio stabilizes to R, which is bigger than 0, then the convergence of S and T is equivalent, right? And that's again for absolute convergence. So for AN, we would write the absolute value of AN if it was a generic one, and then it would be about absolute convergence. The ratio test is the same as the previous one. Instead of limit of those, we simply take the limit of the neighbors, so AN plus 1 over AN. And if we get some Q which is in absolute value less than 1, then we can compare it with the geometric series. And the geometric series we know converges if the Q is less than 1, and then it means that our series S converges by the second test. And similarly we get the root test, right? So if the nth root of the absolute value of n is less than 1, then it converges absolutely. If it's bigger than 1, then it doesn't converge at all. So that's a list of very useful tests. All of them are not that difficult to be proved, and if you want to, you can also have a glimpse on the, say, strengthening of that, because instead of limits we can take what we call limes superior, and either limes superior or upper limit and lower limit. And if you have a sequence, so you can look for all the limit points of the sequence. So that's the values where some subsequence converges to. And the biggest one might be infinite or minus infinity, and that's what's called upper limit, but it might be also finite, right? So for example, if you have a sequence where you have infinite number of ones and minus ones, then the upper limit will be 1 and the lower limit will be minus 1, right? So, and you can replace in the ratio test and in the root test, you can replace the limits with limes superior, which is sometimes very useful. Another thing, coming back to those which are not absolutely convergent, we have got the concept of the alternating series, right? The alternating series are these, and these are the series where the ANs are non-increasing and non-negative, and I take them with plus and minus signs one by one, right? And this is alternating series, and there is a very simple theorem saying that alternating series always converge if and only if the necessary condition is fulfilled. So if the AN goes to 0, it simply converges. But it's very important that you really have both of the properties. So it must be non-increasing series of positive numbers, and you take them with minus 1 to n coefficient, right? And the proof is very easy. So here is nothing to be worried about, so you can go at. It's also interesting to answer question how fast the convergence is, because the convergence rate is something which we are really interested in, right? Because in the computations, in the numerical analysis, if you work with your data, you want to know how well you compute, you of course have to know where to stop in counting the partial sums. And the convergence rate comes very nicely from the comparison test. So if you have the ratio or root comparison test, in both cases, what we do is we compare with the geometric series, right? So geometric series, I didn't remind this, but that's the easy one. So you have sum of q to n n goes from 0 to infinity, right? So it's 1 plus q squared plus etc. And because we know that if you take 1 minus q times 1 plus q plus and so on qk, so it's easy to see what this is. What is this? So you take one this guy as a whole and one the same thing, just with power shifted by 1. So it remains 1 here, everything else gets cancelled. That's called the telescopic cancelling, and in the very end you have q to k plus 1, right? And so you see that the partial sums, so this guy equals 1 plus qk equals y minus q 1 minus q to k plus 1, right? And now if q is less than 1 in absolute value, then the limit will be well, is it right? No, just the other way around. Sorry. 1 minus q to k plus 1 over 1 minus q, right? And you see this goes either to infinity, or it goes to 1 over 1 minus q. And the second case is if q in absolute value is less than, well, if it's real, it goes to plus minus infinity, right? If I would take it absolutely for the complex numbers, it would be just always plus infinity. But the interesting case is if q is less than 1 in absolute value, and then we see the result. It's this one, and you also see the rate of the convergence, right? So how fast it converges, because you know what's left there, and this is what comes in here, and you can then see that you simply see that the difference between the nth partial sum and the infinity in absolute value is a constant times the number r which came from the rate, and r is anything between our q and 1, right? And therefore you need q to be strictly smaller than 1, so that you can find some r in between q and 1, and then you get such an estimate. So you see it's a pretty good polynomial. So actually rate of convergence. Well, and the next task will be yet in another video. That's the power series. That's the case where instead of numbers, we may of course take functions, and then the result pointwise is a series of numbers, but in general it gives us a series of functions. And if the particular functions are monomials, then we talk about power series, and that's our next task, next video.